My name is Chris Nurnberger, and I'm here to talk to you this morning about high-performance Clojure. So I'm one of three founders of a small company named TechAscent that's based in Boulder, Colorado. I have a long history. I started in computer graphics, and in fact, my first Clojure repo that's open source is from 2009, and I did computer graphics using Swing. And I showed it to my friends at NVIDIA. I thought it was really interesting to recompile part of the system dynamically, and I showed them things like that. I have a long system of high-performance computing, from computer graphics to GIS to weather prediction, and I've always been performance obsessed even before I started working on a lot of that stuff. And I'm the primary author of Tech.ml dataset, which is a high-performance column major data processing system. And so my motivation for this talk is through years of using Clojure, 15 years of Clojure, I've had a lot of questions about how various things were done. And recently I started devoting time to research into some of the things that I've noticed and wanted to look at. And I want to talk about three things that I've researched in the last few months. So I'm going to start with character file processing, and we're going to move to core data structures and algorithms. And then finally, I'm going to talk about stream processing, which is really talking about a slightly different computational model than what we get with transducing systems. So the first thing I want to talk about is a library named Chard. And it's about CSV and JSON processing. This image is the char. It's the Zerg homeworld from StarCraft 2. And I'm a big fan of StarCraft. I have been for a long time. Played it in the dorms many years ago at a date, StarCraft, not StarCraft 2, at a date that will go unnamed. So Chard, the overall goal was zero dependencies and high performance. And developing TMD, we just run through a lot of character data just by the nature of what we do. I think, unfortunately, CSV is used all the time, and JSON is fundamental. Issues with CSV are how underspecified it is, and there's many different kind of breaking things you can choose or choose not to do in CSV, and the library that is high quality for parsing CSV, Univocity, we found issues with in various data formats. So we wanted something that was simple and high performance, but really reliable. JSON is very simple and it's specified and it was very easy comparatively, but Jackson, the library for it, has just broken our systems over and over again when we upgrade something random and it just doesn't work. And I thought this bottom part, the RFC, the quote RFC for CSV, of which there wasn't ever one, this was done way after the fact, as a quote in it, due to lack of single specification, there are considerable differences among implementations. Which is the RFC version of abandon all hope, ye who enter here. So developing Chard, I basically had a method. I read a lot of code until I had a theory. Then I would implement that theory and benchmark it and repeat. And so I read a lot of code. I read a lot of Univocity. I read a lot of Jackson. I read a lot of Clojure's Java. And I read a lot of OpenJDK source code. And I discovered that, at least in OpenJDK, the main system that a lot of people are using to parse character data, the pushback reader, which has a nice interface, has some unfixable performance issues. And I'm not sure which line, this is its actual read method, and I'm not sure which line is the problem, but synchronized per character synchronization is not ideal. I have to even wonder, like, when are you going to get the right answer ever? If I have 1,000 threads reading from a character file and they're all reading character at a time, like, is that ever going to be a problem that we need synchronization for? So in any case, I realized at some point that you pretty much have to develop code that looks a certain way, although you can hide that certain way behind some simple functional abstraction where we get the current buffer from the reader, and then we iterate through the buffer character by character. And this is a C-based way of doing it. It's error-prone, but it allows Hotspot to see exactly what you're doing at every point in time. And for CSV and JSON, and I think also for Eden, we don't ever have to push back more than one character at a time. And that changes the design a little bit. The second thing I found, and that was the major one, that right there got me really close or winning the benchmarks in a lot of cases, being very, very careful of how I read the data. But the second one I found was canonicalizing map keys directly from the character buffer. And so what we do is we pull the data into a character buffer, and then for the same logical character buffer, so the same character buffer with the same content, we'll return you the same string. And this is useful because the JVM caches hash codes on their strings. And so the next thing you're going to do is put that key into a hash table, of course, and we've already generated the hash code for it. That was like the final key, and I discovered that profiling Jackson for various cases where it was faster and I didn't think it should be. Interestingly, that same type of optimization works for keywords. It also makes, if you want to do, key-fun keyword, which is what we all do when we parse JSON, it makes that considerably faster, and it would work parsing Eden as well anytime we were parsing something we expect to be canonical, so symbols, keywords, and strings. So here's the end point of chard is you can see it's quite a bit faster than data.json. It's somewhat faster than JSONista in this case, and if we use it with the next thing I'm going to talk about, the immutable data structure system in Ham-Fisted, then we can get a bit faster overall. There's other places we use pushback reader and Clojure. The two I want to highlight are the ones, the Eden reader and Lisp reader, but I think there's lots of chances for higher performance throughout the system, but for sure if anybody's parsing huge blocks of Eden, I think there's a good win to had to changing the way that we parse things, and at least writing a pushback reader that's a little higher performance. So the second thing I want to talk about is Ham-Fisted, and I wrote this to be a high-performance substrate for Clojure. So I just had a lot of questions about how Clojure worked and other choices we could make. And the core of high-performance Clojure is simply speeding up things that we do all the time. Ham-Fisted is an open project, and it's built to question every assumption and have performance profiles and figure out the negatives behind doing things differently. It's biased towards large in data volumes, so there's often times when I'll pay a price for dispatch, checking the things that you're passing in to see how they're done. And I implemented all the core data structure sets and maps, and I implemented many of them many different ways. Speaking of maps, those are the things that I cared about a lot, and I spent a lot of time studying maps. The way that there's some primitives that Java has for maps that are unique, and they're the compute set of primitives, compute, compute of absent, and compute of present. All the maps in Ham-Fisted are able to transition from a full implementation of Java util map to a persistent map in Clojure and back to a transient map in Clojure. So they start with a very wide interface with a lot of primitives, and you can transition them with full structural sharing to a persistent interface, and you can transition that back to a transient interface just like you'd expect to do with a Clojure map. And they all use parameterized hash inequality. And that was because for various use cases, you do want different definitions of hash and equals. You can short circuit in a lot of cases. And I was just curious about hash codes, as we'll talk about later. I implemented the bitmap trie from Clojure. So this is similar to what Gadi was talking about earlier, where the core idea is that we're going to use some in bits of the hash code to decide where in a flat array that thing's going to go, and then the children of that node will use the next in bits of the hash code to figure out where they go, so on and so forth, so it forms a flat-ish tree structure. I would imagine most people in this room are familiar with that. That's a huge part of Clojure is the sort of bitmap trie hash maps and sets. Because the hash is embedded in the tree structure, that gives us a theoretically really fast union and intersection, and all the set operations can theoretically be made really fast, especially in the case where the trees are disjoint. So there's some differences. There's another, Clojure switches from a packed array storage. So if a node has 3 objects, it uses an array of size 3 to an unpacked array when there's enough things in the node. I didn't do this because it would have made implementing the union and difference and set operations a lot more difficult and a lot more error prone. And the other thing I do is I always allocate arrays on powers of 2, and that wins in some cases and loses in others, and we'll talk about that in a minute. One thing I had questions about was the integer hash algorithms in Clojure. I show the difference between what the JDK does and what I do, or what Clojure does here. I thought the OpenJDK's fix, basically JDK just returns the integer, or in the long it XORs the highest 32 bits into the lowest 32 bits. And it fixes cases where your integers only differ in the highest 16 bits by XORing those yet again into the lower 16 bits. So it has a quick hack to make this work well enough in a lot of cases. It's extremely simple to implement. It also uses the comment in the OpenJDK about this hack specifically is there's known cases when we use floating point numbers in hash tables, and I kind of feel like if you're using a floating point number as a key in a hash table, that should be an exception, just outright, and it should just never let you do that. So that's not a performance case I would have personally fixed. So as I said, I also wanted to try, after implementing the bitmap tree and thinking about it for a while, I wanted to try to see what happens if I just used a traditional hash table and use that as a persistent data structure. So it's a kind of take on copy on write, but I use the same leaf nodes as I do in the bitmap tree. So when you do the copy on write, I'm not copying all the leaf nodes, I'm just copying the object array. An object array copy in the JVM is a heavily optimized operation, as you can imagine, especially for power of 2 object arrays. And so the hash table I wrote with equal and hashcode as the hash code provider achieves the same performance as Java util hashmap for all the cases that I had the time to make sure it did for. And that means it has very fast compute and compute if absent calculations. And those are things that are really important for some of the algorithms that we like to do. So another detail of traditional hash maps is resize can be pretty expensive. But what the OpenJDK does, because they're always allocating storage on a power of 2, we know that if we're going from a hash table whose backing store is a size 16 to a hash table whose backing store is size 32, for every element in the size 16 hash table, there's only one of 2 positions it can go in the larger hash table. And so we know it either stays exactly where it is, or we know that it moves 16 positions forward in the map. And that leads to a very elegant, I thought, and efficient resize algorithm, and it made resize completely fall off the profile to where I never see it anymore. So getting to these graphs, I normalized all these graphs in terms of Clojure's time when you just do a kind of naive, put everything into a transient map or use map time. So everything's compared against Clojure's base time. The things that are above are slower. The things that are below are faster. And the way these graphs are written, because they're normalized against Clojure, it overemphasizes slower and underemphasizes faster. So just keep in mind that, for instance, twice, basically anything that was at the 0 position would be infinitely faster, but infinitely slower is not presented on the graph. And that's just a fact of reciprocal math. But that being said, so moving on, in this first set of hash tables, I'm not sure how well you guys can see this, but the first set of hash table comparisons, all the hash maps are grouped in one place at the bottom, and they're about twice as fast. And the bitmap tree I wrote does better for smallish n, and worse for larger n. And I think that's due to the array optimization, but I'm not really sure. For access times, again, you know, the hash maps, the flat hash maps is what I like to call the traditional ones. They all have pretty fast access times, so does Clojure Data Int Map. And then the trees are grouped together and they're fairly close to each other. Reduce, I put this graph here to make a point during the talk, and that reduce is lightning fast on every hash map. What I didn't show is the overall time this takes, but quite honestly, reduce is so fast, iterating through the data structure is so fast in every hash map that the pure iteration time is never something you should be concerned with, whether you use a bitmap tree or a flat hash map. They all iterate just lightning fast. And I also compared in-memory map size, and this is where Clojure had a distinct win across the board. And I thought that was interesting. Part of it's because they always store their data in packed arrays. They're not using power of 2 allocation. But overall, it's interesting to me because people have criticized Clojure for using too much memory, and they use these generic kind of large terms. But clearly, Clojure is pretty memory efficient, at least in a lot of cases, depending on how you use it, in its current form without any optimizations. Moving on, I want to move away from, so those are all granular operations. And the biggest win I got in some cases was like basically a factor of 2, maybe a little bit more. I want to move on to like more aggregate operations, and I want to talk about a new primitive that we haven't talked about, and it's a generalization of reduce, where we're going to do a group by and we're going to do a reduction at the same time. So when we want to put an incoming value into a hash table key value pair, we're going to use a function on the existing value with the new value before we put it in. And this allows us to iterate over infinite data, essentially, if our reduction function is reducing to, for instance, incrementing an integer or running some count of cardinality or something like that where we have more or less fixed size at the nodes. We use this all the time. All of us has used frequencies, and all of us have used the base group by. So I think on the slide, yeah, group by is group by reduce with conj bang, and frequencies is basically group by reduce with inc, where you're just inking the current value up by 1. So looking at frequencies specifically, I compared, this is the frequencies algorithm. If you go look at frequencies, the source code to it, it's about this. With a fully mutable version of frequencies. Now remember, when I do mutable things, I can always switch from mutable to immutable with the persistent bang call. So they implement iEditable collection and that form of things. But I specifically went down the path of finding like the fastest way I could think of doing it, and that is doing a fully immutable pathway with compute of absent primitive. So here is the performance of that, and you can see anything that implements the compute of absent primitive is on the order of like, I wouldn't say, the bitmap tree is not quite there, but you can get to 5 to 10 times faster, and this is for serial frequencies. If I parallelize frequencies, it's more than this for big N, but less than this for small n. So it kind of depends on what n you're looking at, but frequencies showed a nice win by using the compute, basically the compute primitives. Then we moved to union, and for union specifically, for set ops, I moved the whole operation into the hash table. And so my hash tables have a .union member that you can call on them. And that, especially for hash tables of the same type, showed a major win whether I had a bitmap tree or not. And the bitmap trees were faster for the disjunct case, but the regular hash maps, when union was moved into the hash map, was faster for the case where there's a lot of overlapping keys. And this is, reduce union is something that we do a lot of. So what I should have said about union is having a fast union allows you to parallelize building your hash maps. And so in the cases where I have a whole lot of data and I want to process a lot of data in parallel, I can essentially generate a hash map for each thread context, and then I need to union those together in kind of a scatter-gather type operation. And so union reduce is crucial to dtype next performance, and it's crucial to TechML datasets performance. So this is a primitive that I actually use quite a bit. And you get a big win in this case when you move the primitive into the hash table, the union primitive in the hash table. I also tested in this case, what if the left-hand side of the union is transient? And oddly enough, that didn't show that much of a win. And I don't know why, but again, this is serially reducing many hash tables into one, which is something that happens usually at the end of a run where I've broken things up into many threads and I've produced a sequence of hash tables. A new primitive in Clojure is update vals. That was added in, I think, 11.1. And this is another primitive where whether I implement it in the hash table or I implement it in the persistent vector layer, persistent vectors also support update vals. You got a big win by moving that primitive into the data structure itself and implementing there, as opposed to using the transient primitives to implement it. So here's one that's not a data structure operation. This is an algorithmic operation. This one matters a lot to some of you because sort is in log n. Everything else we've talked about till now is big O of n, more or less. But sort's in log n, so this is in some ways a much more important thing to optimize, and I found that FastUtil's parallel quicksort is lightning fast. I didn't find that it made much of a difference whether I put a bunch of objects, doubles as objects into a big array or whether I used a double array. The parallel quicksort dominated by quite a lot, and you can see this graph is getting faster comparatively as it goes on. And what Clojure uses is objects.sort, And the last time I checked in JDK, object.sort is temsort. Potentially, if you parallelize the temsort and then use the same merge that FastUtil uses, you would end up with a good win that was a little more robust. We know that Quicksort has some problems that degrade into bad performance, and temsort is much more robust. But I just think this is important. FastUtil has a core library where you don't have to rely on all of their specializations. It's a much smaller jar, and I think this might be an option to move into Clojure Core and move sort over to it, specifically sort and sort by, because I think we'll get a win in most cases there. So the third thing I want to talk to you about, and maybe the most abstract thing, is I want to talk about Monte Carlo simulation, and you'll see how this might or might not relate to your computational models that you're running now. Monte Carlo simulation is a class of simulations where we're sampling from a distribution, so we have an infinite stream of numbers, potentially. And so the way it works is we repeatedly pull values from a distribution, and we combine them in various ways, usually with simple arithmetic primitives. And it's sort of probabilistic programming on the cheap. I know that there's some people here who are literally experts in probabilistic programming, so you can catch me after the fact and tell me how wrong I am. But I think it's a programmatic model that generalizes to other Clojure systems. And streams are lazy non-caching, so that's the same as transducers with eduction, if we're double erroring along eduction. And they can be either limited or unlimited, and I pass whether they're limited or not through the processing chain with a protocol. And if they're unlimited, then they have much faster compositional qualities, which is something that I found surprising, but it makes sense in retrospect. It's because you never have to check has next. And that leads to not having to copy the data into intermediate arrays before I call map on it, before I essentially apply the map function operator on it. Another aspect of streams, which is a detail, is that they automatically broadcast and they operate in double space. So an expression like plus AB 2.0 will broadcast that too and make a stream out of it essentially. So you don't have to call repeatedly on constants or create a custom plus operator when you want to add a constant to a stream of values. And so here we're looking at the actual detailed difference where if we have a map on a limit versus if we have map on unlimited streams. And so in the limited case, I'm going to apply a map function to y streams coming in. So I need to create an array of y length, and I need to copy the values into it if its iterator has that value, or exit the iteration if it doesn't. In the unlimited case, it's much simpler. I can just create the arguments I'm going to pass in the function outside of the application itself. And I can just pass the same exact function array, essentially, to each map operator. So this is the core reason of why processing with unlimited streams can allow you a faster computational model than if you have to check every time. Now, in some cases, that just means your map operator will have to check. But in some cases, it won't. So that may actually have a meaning for you guys when you're processing, for instance, large streams of JSON or something like that coming in. Here's a stream operator. So this is how we define plus or minus. And the thing that's interesting here is for the higher arity definitions of plus, we move to a different definition of map, which can take more advantage, basically expects a function that takes a list already. It's not calling .apply or .apply_to on the IFN implementation. It's expecting a function that just takes the list in the first place, which in a lot of arithmetic things is just easier to deal with. So, as I said, and we'll see concretely, unlimited streams have a generally faster compositional model. And this was really surprising to me. It's very surprising to me that just the if check, the has next check can mean so much, but that means unlimited streams conceptually have a very similar computational model to channels. We know in channels that they use nil as a sentinel. So in the stream, if you try to read from a closed channel, it'll return nil. That's also an unlimited computational model in a lot of ways. And as I said, it has two different map implementations, which I think is wise to switch to a different version of map for higher arity applications. and it works in doublespace. So here, all I'm doing is running the expression in here and calling reduce on it with a trivial reduction operator that just returns its input every time. And already we're seeing quite a bit of performance difference. And I wanted to highlight dtype next is very carefully written for performance, as many of you know, and the stream library is written for performance. But if I hand implement the reduction in Java, at least on my Mac M1, the typed definition is slower, or at least not faster than the untyped definition. And so this is JDK 19, and I literally can't figure out how this works, because for the untyped definition, it should have to box a double and do a bunch of other things, but JDK 19 is getting better and better at handling untyped generic code, which has a lot of implications. A lot of the work I did in dtype was ensuring that when you say plus on a bunch of things that could only have doubles, it does a double-specific plus on it. And it looks like in some cases that work was for naught because JDK 19 is getting better and better at optimizing these things out. And so here we look at simply creating a double array from a simple application of plus to 4 different streams. And in this case, I have to admit I'm kind of picking on Clojure. I knew this wouldn't perform well for a couple of reasons. Number one, higher arity map is definitely slower than map that's specialized towards 2 arguments, and it's slower in every case. But number 2, the double array operator I know isn't optimized as much as Ham-Fisted's double array operator. So in any case, I was picking on Clojure a little bit, but I was surprised at the performance difference here. I thought this was extreme. And so dtype next and the stream library are over 20 times faster than Clojure for this simple statement. And they all produce a double array at the end of the day. And then the inline definition, which would be really tedious for you to take like an abstract source tree and create inline definitions all over the place, in my opinion, isn't that much faster than dtype, not enough faster to make it worth it. So kind of the best you could possibly do at NVIDIA, we used to call this speed of light, which has the wonderful acronym of SOL, which, especially when you're dealing with hardware, if you're going the speed of light, you probably are also out of luck. Because you know, the hardware will heat up, and then your timings are different, and then things hang, and it's over, the game's over. But anyway, here's the speed of light in this case isn't that much faster, and that's just something I like to do a lot of times when I'm doing any problem I like to solve. If it is at all performance-oriented, I like to literally do a minimal version of it as low-level and fast as I can. And then if it's faster, I want to back off that low-level approach until it has, you know, a reasonable implementation that's not too nasty to carry forward. And so here, I want to put all the toys together that I've just talked about all at once. Here, we're going to talk about binning a lot of doubles. And so this is a case which is always going to be high-end. You need a lot of doubles so you can have a bit of sort of statistical confidence in what you're doing. And we sample them. And sample is type hinted to return a double array, although in this case it really doesn't matter. We run through it exactly once and pull the min and max out at the same time. And then we do a frequencies, and frequencies in this method was the slow point. So for 1 million doubles, the frequencies call was the slow point. And then we sort by, and I've already talked about the optimizations that I've done to make sort by as fast as possible. So here's the implementation of frequencies, and basically I'm using, the reason you see a lot of like hamif function, hamif by function, those are just helpers to create the actual Java API primitives that are defined in the java.util.map interface. So I don't have to remember them, or I don't have to type them more than once. I do a mutable increment of the thing, like we talked about, and the one thing in here that we haven't talked about is preduce. So preduce is to reduce what pmap is to map. And it takes more arguments because it breaks down the things you need for a parallel reduction. So instead of an initial value, it takes a function that can produce an initial value per thread context. And it takes an extra function that is kind of like your reduction function, 2 things into one, but that's for merging the results of your final reduction into a final container that you're going to return after you've done your parallelized reduction. And of course, I'm using the union operator in ham-fisted, which will do the right thing regardless of the map you put in. It's called mute map union, but it does the right thing regardless. But I just thought it was interesting to show you this isn't that much worse than frequencies, but it is double the length. It'll also perform significantly better as your N increases over time. And we're all moving to worlds where the N's going to increase by a lot over time. So wrapping up, there's a lot more in ham-fisted that we could talk about. You know, the library is still in beta, but even when it moves out of beta, it's a library that I wrote for exactly high performance and use cases that I need. If we wanted to make it really robust across the world of use cases possible, then it will take help from outside people. But it has very fast array wrappers, both fixed and global, that wrap primitive arrays of every type. It's got a lot of, its object array method is highly optimized. It turns out I do use that quite often in TechML dataset. I'm not sure why, but it also has ways that you can just wrap an object array in place with an immutable wrapper. So you don't need to copy the object array into a persistent vector before you hand it to the rest of Clojure, and everything will work out just fine still. It'll have the same hash code, but it can't cache, you know. It'll have the same hash code, it'll have all the same things, it can cache the hash code. But I thought that was useful because we've had processing situations, for instance, using Clojure.string split, where we were splitting big chunks of text and just creating the persistent vector from the big chunks of text after they were split ended up showing up on the profiler. Sort and sort by are parallelized and a bit faster. As you can see, I've already talked about the hash maps. I have a very high performance version of Memoize that's based off caffeine, which I think probably replaces a lot of the uses of Clojure.core.cache, depending on if you're going to use the cache as an immutable data structure after the fact or not. But it's very useful for me because it contains weak and soft references, and those are really difficult to get right. As anybody who's used them knows, like if you ever get the value and lose reference of the soft reference, it could be the value, you could return something that's nil before you know it, basically. It's the opposite. When you use soft references, you need to maintain a reference to the value the whole time and the soft reference. So now instead of returning one thing, you need to return two in some cases. Or if you only have a reference to the soft reference and you're under a lot of memory pressure, which will only happen when you have a ton of people hitting your system and you're trying to give a demonstration, then all of a sudden it'll return nil where it never has before, and you won't, like, you'll be at the podium wondering why. It has group by reduce and compose reducers, and it has, you know, as I said, a whole parallelized reduction architecture that works on any Java util thing. So it's split iterator, it can be split iterator based, it can be indexed based. It's got an implementation that works with Clojure's fold primitives that you can pass into persistent maps. It's just a generalized reduction architecture that's made for parallelization. So this is kind of the big picture. I think that it would be interesting, and one thing I'd like to see is if we had a set of open a profile performance suite that we could run, that we could all optimize. So if you think you know something that might make Clojure faster in various cases, you could just plug it in and you could see, basically plug it in at the language level, and you could see if it actually ran better on the set of use cases. So something I've seen suggested is for persistent vectors, you know, check the hash code before you actually run equality on it. That has a bunch of drawbacks because you may not have calculated the hash code, so you'd probably need something that would tell you whether you calculated the hash code or not. But in any case, it would be interesting to me if we had an open performance suite that we could all work on over time. Potentially there are some big wins in there, and I hope I've convinced you of this, you know, already. But the other thing I want to note is that a culture of high performance does not necessarily conflict with the culture of minimalism and simplicity that Clojure already has. There are times when having things that perform much, much better than what they do now leads to an overall systematic design that's far simpler, because you don't have to work around, you don't have to add intermediate caching layers, you don't potentially have to have your lambdas take forever to spin up because they're calculating something random. You, for instance, you can calculate indexes really fast because I've showed you fast ways to construct and join hash tables. So there's times when having really high performance makes your overall systematic design simpler. And so it can be a little verbose when you're writing the high performance primitive yourself, but then you just steer everybody to use a high performance primitive, and you can end up with a simpler system overall. The other thing I want to note is that our AWS bills aren't reducing anytime soon, and they're likely to keep climbing, and power is likely to get more expensive, at least in the short term. So we all know all the problems with power that we have. Like, it's one of the dirtiest things that we have to deal with, unfortunately, as mankind. But being very precise about how we use our machines can allow us to scale to higher volumes and use less power and be friendlier not only to the earth, but clearly to our neighbors around us. So with that, I want to wrap up. This is my son, Aster, and I love the expression on his face here. Yeah, that's my talk. I hope you guys enjoyed it.